Welcome back. We are on none other than lesson 10-1, titled Compositions and Congruence. And we are going to focus mainly on compositions of transformations. So activity 9 is all about those three transformations we've learned, which are, we started with the translation, or onion. We looked at the reflection, and then last we looked at the rotation. And these are all, of course, rigid motions because the size and shape is preserved throughout the transformation. And so composition of transformations is really just putting them all together, or in other words, doing multiple transformations back to back. So we might do a translation, then a reflection, or a rotation, then a translation. And so that's really all a composition is. It's now multiple transformations together. So let's look at our learning targets, figure out what we're going to learn. We're going to find, looking for something, the image. Remember, image is the figure after the transformation. So we're going to find the image of a figure under a composition of rigid motions. So we're not looking at non-rigid motions. So all of our shapes, the size and shape should be preserved. So we're just going to be looking at several transformations back to back. And then we are going to also find the pre-image of a figure under a composition of rigid motions. So if you think about that, they're going to tell us where it ended up by giving us the image, and then we're going to figure out where it began. So work in reverse order. So if you would, go ahead and draw a line. Let's start this off easy. Go and draw a line above number 1. Take a minute to read through the text before continuing with the video. Okay, hopefully you've taken a second to read through the text. You notice I've highlighted a couple things. So it says, consider the series of transformations. And that's all a composition of transformations is a series of 2 or more transformations performed on figures. So they're telling us that what we're seeing up here with our pre-image is that it undergoes a series of transformations to end up at this point here. And it tells us what those transformations were. It said the first is, remember, a capital R stands for rotation, not reflection. Remember, I know we have 2 transformations that both begin with R, but capital R stands for rotation. So they tell us it's a rotation about the point 46, that's the center, and a negative 90 degrees. And they also remind you when it's a negative 90 degrees, that is considered a clockwise rotation of 90 degrees. Recall that. Remember we said if we had the X and Y axis, the reason that is if the angle opens up, that's actually a counterclockwise motion, and that is a positive degree. And if it opens down, if the angle opens down, it's considered a negative degree, or counterclockwise, clockwise. So negative 90 is considered a clockwise rotation, about the 0.46. And then the second, so that's what happened here. They rotated this arrow 90 degrees clockwise. That's why it turned and faced to the right, about the 0.46. And then the second transformation is a reflection. The lowercase r stands for reflection across the line y equals 0. And what I love to point out about this is that they tell you what that means. It's a reflection across the x-axis. If you did not know this, the x-axis actually has an equation for the line that runs through it. It is the equation y equals 0. Because what does y equal at every single coordinate on the x-axis? 0. And so they're telling you that this image here reflected across the x-axis, the line y equals 0. So just for a little future help, if the equation for the x-axis is y equals 0, what do you suppose the equation for the y-axis is? Well, it's kind of the opposite. Look, the x-axis, the equation is y equals 0. So the y-axis is the line x equals 0. So you'll see that they don't actually specifically say, hey, reflect across the x or y axis. They'll use the linear equation for the line on the x or y axis. In this case, it's y equals 0, which is a reflection across the x axis. So the next thing we're going to learn is how that composition is written. The notation for composition of transformations is similar to the way you express the composition of functions. I'm not sure if you learned composition of functions in Algebra 1, you will definitely learn them in Algebra 2. And so the composition pictured above is described by the following. Notice what's interesting about the composition is we actually read or see written first a reflection across the x-axis. But if we go back and look at the text, the second transformation was actually a reflection across the x-axis. So what they're telling us, the way we read a composition is we actually start within the parentheses. If you keep reading a little bit further, it says, notice that the transformation that occurs first in the series is in the interior of the notation. So when reading the notation for composition of functions, start inside the parentheses, just like PEMDAS. We know with PEMDAS, the P stands for parentheses, start in the parentheses. So this composition of functions, we're going to start in the parentheses, and it tells us it rotated 90 degrees clockwise about the point 46, and then it reflected across the x-axis, or the line y equals 0. So keep that in mind as we write a composition of transformations. Our first transformation is written inside the parentheses, and then any other transformation is written to the left of it. So keep that in mind as we move forward. So with all those things, draw a line at the bottom of your page and complete items 1A through C before playing through the video. So hopefully you took a second to complete this on your own before continuing playing through the video. So number 1A says a clockwise rotation of 60 degrees about the origin, which the origin is located at 0, 0 on the coordinate plane, followed by a translation by directed line segment AB. So we're going to perform a rotation first, then the translation. So if you notice here that we have the rotation about the origin, 60 degrees clockwise. Remember, clockwise is negative degrees. It is inside the parentheses. Then on the outside, to the left of it, we wrote a translation of the directed line segment AB. And then I put this OR here because we actually do have coordinates for AB. So look at the coordinates of AB. If we start at 0 on the x-axis, and then go to 1 on the x-axis from A to B, we have gone a positive 1 on the x-axis, or to the right 1, if you think about it that way. And likewise with our y values. Look at the y coordinates of these 2 points. If I start from A and go to B, well, if I start at 0 on the y-axis and go to 1 on the y-axis, I go up 1. So another way to represent translation, other than just saying directed line segment AB, we can actually give a specific direction. It looks like a coordinate, but what this really means here is that we went up 1, and, or excuse me, left, or man, I'm all over the place, right 1, and then up 1. Because our x value is positive 1, our y value is positive 1, that's really just telling us the distance and direction to go. Right 1 and up 1. So there's 2 ways to represent translations. We could either simply say directed line segment AB, although that doesn't really give us much information, or we can say what looks like a coordinate, positive 1, because this translation will, of course, move right 1, then up 1. So let's press on to part B, a reflection about the line x equals 1. So that's the first transformation we're going to do, followed by a reflection about the line x equals 2. 2 reflections, so both using lowercase r here. So reflection across x equals 1 goes inside the parentheses, and to the left of it is a reflection across x equals 2. We're just learning the notation here. And last, and certainly not least, 3 translations, each of directed line segment AC. Remember, it is important that they say AC, not CA. Because depending on where those points are located on the coordinate plane will tell us the direction. A to C is actually a different direction than C to A. So we could either write it like this, where these 3 translations back to back, all using directed line segment AC, or let's go back and look at the coordinates from A to C. If we're going from A to C, I see that my x value did not change. So we don't go left or right at all, since the x value of both A and C are the same, but look at our y values for a to c. If I start at 0 on the y-axis and go to -1 on the y-axis, really I'm going down 1. So another way to represent directed line segment AC is to use this notation, where this means we don't go left to right, we just simply go down 1 unit. So we can represent it two ways. I prefer this way because it actually gives us the direction in the notation instead of simply saying use directed line segment AC. So now that we're learning the notation a little bit, of course, go back and reference this as needed. Let's see if we can actually use that notation to draw a composition of transformations. If you would, go ahead and draw a line below number 5. Remember what the line tells us is we're going to pause the video, work all the way to the line on our own before playing the video through. So pause the video, see what you can come up with, look at the notation here, go back and check your notes on the previous page, and see if you can complete 2 through 5 before playing through. Okay, hopefully you've taken a second to try and complete items 2 through 5. What I want to do is try and show you, remind you how to perform rotations, especially when the center of rotation is not the origin like we see here, where the rotation is around the center 4, 0. So I want to remind you how to do that. So I'm going to go over to another screen, and here we have that same arrow. Now, I want to show you or clarify something. Each of these squares that you see here, or each of these units, are actually 2 units wide, just like the one you see on the lesson itself. So just wondering why this says 4 when it's only the second square is because they're 2 units wide. So I've labeled a couple key points on this arrow, and that's what I'm going to use to rotate 90 degrees counterclockwise around the point 4, 0. I'm going to use these specific points. So starting with A, which is located at 2, 2, 4, 6, so 2, 6. The first thing you do, and recall, is we're going to subtract our center of rotation, which in this case is, let me actually check, I believe it's 4, 0. Correct? 4, 0, not 0, 4. So this is the point in green, 4, 0. So we are going to subtract that center, 4, 0. 2 take away 4 is -2. 6 take away nothing is 6. Then we're going to perform the function. Now, if I need to rewrite that function for you, every point goes to rotated 90 degrees counterclockwise. I believe the y and x swap, but we change the first sign. So that's what we're going to do here. We're going to take the point -2, 6, and we're going to swap those two. And then change the first sign. So it'll be located at -6, -2. And then the last thing we need to do is add the center of rotation back. So we'll add the point 4, 0 back. So -6 plus 4 is -2, and -2 plus 0 is -2. So point A, after the rotation, 90 degrees clockwise around the point 4, 0 would be at -2, -2 right here. Remember, it said that we wanted to reflect across the line x equals 4, which is right here. This is the line x equals 4. So when we reflect across that line, again, on a reflection, however far a point is from the line of reflection, that's how far it goes on the other side. So if you see here, this point is located 2, 4, 6 from the line of reflection. So we'll go 2, 4, 6 on the other side of the line of reflection, and we'll just simply label that A prime. So that's where A prime is going to be located after the rotation and the reflection. We'll do the same thing with our other points. So we'll move on to point B. B is located at 4, 2, 4, 6, 8, 10, 4, 10. So again, we're subtracting our center of rotation, which is, in this case, 4, 0. 4 take away 4 is 0. 10 take away nothing is still 10. We're going to use this function here. So that tells me to swap my two numbers. and then change the first sign, which was the y. And then we add the center of rotation back, which is 4, 0. So negative 10 will add 4. We get negative 6. 0 adding 0, we still have 0. So B prime will be located at, not B prime. And so we still have to perform the reflection. But negative 6, 0 is right here. So however far that point is from the line of reflection, that's how far it has to go on the other side. So if it's 2, 4, 6 units, or 2, 4, 6, 8, 10 units from the line of reflection, we need to go 2, 4, 6, 8, 10 on the other side of the line of reflection, which would put this point here at B prime. Now, TBH, and we all know what TBH means, we could continue repeating this process with point C and point D, but we do know that these two transformations, rotation and reflection, are rigid motions. So we know that this arrow is going to look the same as the pre-image. So we could, in fact, we already know that these 2 points connect like we see here. And so we can actually connect those points. And, well, before we get ahead of ourselves, let's go ahead and finish finding C and C prime. So C was located at 2, 4, 6, 2, 4, 6, located at 6, 6. So we are going to subtract our center of rotation, which is 4, 0. 6 take away 4 is 2. 6 take away nothing is 0. Then we will perform the transformation. So we are going to swap x and y. So 0 goes to 2. And then change the sign of our first number, our y, but changing the sign of 0 is nothing. And then the last thing we'll do is we'll add 4, 0 back. 0 add 4, we get 4. 2 add nothing, or 0, we get 2. So after the rotation, C prime, this other point over here, is located at 4, 2. Which is right here where D was. And then once we reflect, since it's on the line of reflection, something caught me off guard. Let me go back and check my work just a little bit. So C is located at 6, 6. So we subtract the center of rotation, which is 4, 0. 6 take away 4 is 2. 6 take away 0 is 0. Then we switch the 2, we get 0, 2. And then C prime should be located at 4, 2, which would be right here. And after the reflection, it should stay in the same place. What am I missing here? C is located at 6, 6. We subtract. Let me pause that. Okay, so I figured it out. Those of you actually watching this video, I was wondering why this point didn't move. 6 it happened back here. I apologize for that. But it does happen. Mistakes definitely do happen. But I'm glad I figured out that something was definitely not working. 6 take away 0 is actually 6. So then we use the function, swap the 2, and we get 6, 2. And then change the sign of the negative 6, or change the sign of the 6 to negative 6. And then we add the center of rotation back. There was the problem. 6 take away 0 is actually 6, not 0. Negative 6 plus 4 is negative 2. 2 plus 0 is 2. So after the rotation, C prime is located at negative 2, positive 2, which would be here. But again, we have to reflect over the line x equals 4, which is this dotted line here. So this point, C prime, before the reflection, is 2, 4, 6 units away from the line of reflection. So we need to go 2, 4, 6 on the other side of the line of reflection. and this is where C prime will be located. So we can actually see the tip or the triangular section of our arrow. So if we want to, knowing it's a rigid motion, both of them are rigid motions, we can actually continue this by finishing out drawing the image of our arrow after a rotation 90 degrees clockwise about the point, counterclockwise about the point 40, and then reflection across the line x equals 4. So this is where our figure should end up on our coordinate plane. And then if we hop back over, that was item 2. What they want us to do with item 3 is draw the image of the arrow mapped by a composition of the same transformations in the reverse order. Now, if you notice, I've already graphed that here. Item B, you're literally just doing the exact opposite. So you're going to reflect this over the line x equals 4. Well, if you think about that, I'm not actually going to graph that for you. But if you think about it, if this arrow is reflected across the line x equals 4, this corner on the right-hand side is actually going to map here on the other side of the line of reflection. And when we learned about reflections, we learned that points on a line of reflection, such as this point here, the tip of the arrow, and this point here, those points actually do not move. So reflecting this pre-image, that original arrow over the line x equals 4, makes it appear that it hasn't gone anywhere. We use the term map to itself. So with that in mind, all you're really doing is rotating your arrow 90 degrees counterclockwise about the point 40. So you can follow those steps using these coordinates, and what you actually see, I'll graph it on my other graph, is where this arrow was ending up before we reflected on the first one. So this is where reflection across x equals 4, then a rotation 90 degrees counterclockwise about the point 40. So this is where it would have ended up. Because again, a reflection across x equals 4, this pre-image arrow would actually not have gone anywhere. It would have mapped to itself, and then we just rotated about the point 40, 90 degrees counterclockwise. So item 4 then says, what single transformation maps the arrow to image A? Write the name of the transformation and its symbolic representation. That's what this is. This is the symbolic representation. So what would map this arrow to A in one single transformation? Well, a rotation negative 90 degrees, so clockwise. Think about it. We could rotate it 90 degrees clockwise about this point 40. So if you notice, all 3 of these arrows, in fact, rotate around this point. So we could have just rotated 90 degrees clockwise to get to A, and then 5, which single transformation maps the arrow to image B? Well, we could have just simply done a 90 degree counterclockwise about 40, which really is what happened, because when we reflected on B, or item 3, when we reflected across the line x equals 4, that pre-image arrow mapped to itself. So let's take a look at items 6A through C. If you would draw a line at the bottom of your page, complete the items before playing through the video. So one of the main things we're seeing here is that the order of a transformation in a composition can affect the position and orientation of the image. So in other words, order matters. We know that from PEMDAS. Order absolutely matters. We can get different answers depending on the order that we choose. So composition of transformations is no different. But sometimes a composition can produce the same image as a single translation, reflection, or rotation. So what we saw up here is that in order to get to arrow A, we could have just simply done a 90 degrees clockwise rotation about the point 40. We didn't have to rotate it 90 counter, then reflect x equals 4, which was 2 transformations. What we're seeing here is that we can actually use 1 transformation. So that's what we're looking at here. So we're learning the notation, but we're also trying to learn what single transformation can produce the same image. So this first translation, the way we interpret it, 1, 0, meaning we went right 1, we didn't go up or down on that one. This transformation, or this translation, tells me that we go up 1. Notice that the y is positive 1, the x is 0, so the y being positive 1, that means we go up 1 on the y-axis. And then this last translation, 1, 1, tells us we're going right 1 and up 1. So a combo of all three of these directions, right 1, up 1, right 1, and up 1. Well, look, we go right 1 twice, so that's technically right 2. And we go up 1 twice, which would be considered going up 2. So the simple way to write all of those transformations combined in one single translation is right 2, up 2. Now, item B, we have 2 rotations around the point 0 or the origin, and they're both 90-degree counterclockwise. So if we rotate 90 degrees counterclockwise twice, what we're really doing is rotating 180 degrees, because 90 degrees plus 90 degrees more is 180-degree rotation. And notice I put this little asterisk here. We don't have to specify positive or negative on our 180 degrees, because positive or negative 180 degrees, we get in the same position. The last one I thought was a little tricky. I even had to draw it over here to understand it myself. A reflection across the line y equals 0. Notice I put the note that really is the x-axis. And then a reflection across the line x equals 0, which is really across the y-axis. So what I did was I drew my original arrow, just an arrow, in the first quadrant. That's what you see here in the first quadrant. Reflection across the x-axis, we would end up in the fourth quadrant, pointing down. And then a reflection across the y-axis, we would end up in the third quadrant, still pointing down. So what we're really trying to figure out is how would I go from this arrow to this one? And I saw that the arrow was pointing up, and then it was pointing down. And from the tip of this, or the base of this arrow, to the base of this arrow, we can actually draw a straight line, or 180 degrees, from these two corresponding points, which tells me that reflecting across the y-axis, or excuse me, the x-axis and then the y-axis, we can perform the same transformation with one single rotation around the origin, 180 degrees. So not only are we seeing the notation, we're learning the notation, but we're also trying to understand what's really going on with these transformations and how we can represent multiple or a composition of transformations as one transformation. So hopefully that's making sense. Pause it, go back to it if you need to replay it. But we are going to press on, and we're going to complete items 7 through 9. So if you would, draw a line right above. You can also find compositions and transformations and complete 7 through 9 before playing through the video. Okay, so the point of items 7, 8, and 9 is really to deepen your understanding of what is taking place when we perform these transformations. So notice on item 7, I said sample, because there's really multiple transformations that we could actually do to map this arrow in this coordinate plane to where it ends up in this coordinate plane. So I said, for starters, remember we start with the inside parentheses, rotate 90 degrees clockwise about the point 0.6. So that'd be rotating around this point right here. So imagine that it rotates around that point and it ends up looking something like this after that rotation. But I still need to move it down so that this bottom or the base of my arrow actually ends up at the origin. So then I said translate 0, -6, which means we don't move left or right. We just simply move down 6. So what I would like in this video, at this point, pause whatever answer you had, send it to me on Remind, and maybe I'll make it worth bonus if the composition actually works. So again, you don't have to go with this sample answer. I just thought this one was probably the more basic one. So then item 8 says, consider the composition you identified in item 7, but with the transformations in reverse order. Does it still map the arrow to the same image? And according to the one I did, no, the arrow would actually be in the second quadrant, which would be up here. So you can see some of these red dots and even this work here. So if I did it in reverse order, in other words, I rotated it, or excuse me, translated it down 6. So imagine I translated this original arrow down 6, and I had this point on the origin, arrow facing this way. And then if I rotated that about this point, still 0, 6, my center of rotation, it would actually map my arrow, and I know it's getting a little confusing, it would actually map my arrow something like this. Obviously, that's just a quick sketch of it, but hopefully you're seeing what would happen here if I rotated, if I translated using this same composition, but in reverse order. If I translated first, then rotated, this is where I'm looking that my arrow would end up. So obviously, order of composition and transformations matter. So then item 9 says, identify a composition that undoes the mapping, meaning it maps the image of the arrow on the right to the pre-image on the left. So what composition could take us from this image back to our pre-image? Let me clean up some of this stuff here. So what could take this pre-image, or excuse me, what could take this image back to this point? And I said simply rotating 90 degrees counterclockwise about the origin, 0, 0, and then translating up. So what that would have done is it would have rotated this arrow 90 degrees about this point. So it would have ended up looking something like this. Now I know it's a crude drawing, just bear with me. And then we would need to shift it up 6 units so that it would end up back here. So what they're trying to get you to see is how we could go in reverse order, or what's a way to undo the original composition of transformations that took this pre-image to the image. So we're going in the opposite direction now. Now let's take a look at item 10. If you would draw a line at the very bottom of your page. Again, try this on your own, even sketch as you need to before playing through the video. So the main idea here is just to really start to wrap our minds around what these transformations do to a figure. We're not even talking about where specifically this image ends up. We just want to know, based on these compositions, can you dictate or can you predict what direction the arrow is going to face? So right now, it's pointing to the right. And so our first composition tells us to translate using directed line segment AC. Now, remember, order matters even with the directed line segment. So if it says A to C, that means we're going to go from point A to point C, that distance. So we're going to move that distance. Let's see if I can do it. Move that distance down. And then we're going to translate using the directed line segment DB, which again is important that they tell us that. So from D to B, we're going to the right that distance. So it'll look something like this after the transformation. So of course, hopefully you said that it would be pointing to the right. Now, part B is going to be a little bit harder for me to show the way I did on A, so I'll have to do a couple sketches here. So our first transformation in this composition tells us to rotate it 90 degrees counterclockwise around point D. So our arrow, 90 degrees counterclockwise around point D, this is our center of rotation, we should see something like this, right? Again, we're not getting exact here, and I know that's a crude drawing, but that's just the rotation 90 degrees counterclockwise around the point D. Then we have to translate it, or excuse me, reflect it, sorry, looking at the other one, reflect it across line D prime, B prime, which of course after the first rotation, this would end up being B prime and this would be D prime. So now imagine we reflected this arrow across this line that's going right through the middle of our arrow. Well, if we reflect it, this point will map here and vice versa. This point will map here and vice versa. And this point and this point will actually stay on that line of reflection. Because remember, points on the line of reflection do not move. So which direction is the arrow going to be pointing after it reflects across this line, D prime, B prime? Well, it maps to itself at that point, so it will still be facing up. The last one we see here, we're going to start by reflecting across the line AC, which runs right through it. And then we're going to rotate 180 degrees around point A. So reflecting across the line AC, again, this is going to be a pretty crude drawing, so just bear with me. This point will map roughly about here. Points A and point C won't go anywhere. And then point D will end up all the way over here where B was. So this is a reflection across the line, AC, and then it says rotate 180 degrees around point A. Well, 180 degrees, we don't have to specify counter or clock. So if we rotate around this point, all of these points are going to move in this direction all the way till it ends up looking something like that. Now, again, that's a pretty nasty drawing of that, but hopefully you're understanding what these transformations do instead of getting hung up on exactly where each point is going to be. Now, obviously, when we focus on the coordinate plane, it's very important where specific points end up. But when we're talking about just a plane in general, where we're predicting the directions, we're not so concerned with where each individual point ends up, but where we believe the figure will be just in general, and which, in this case, which direction it will be facing. Now, let's wrap up our final lesson, or the final page of lesson 10.1, covering the inverse of these transformations. So the last thing we're going to look at in lesson 10-1 is the inverse of these transformations. So it says, like many functions, transformations have inverses, which are transformations that map the image. Typically, remember, the image is at the end of the transformation. So we're going to try to map that back to where it all began at the pre-image. So the inverse of transformation T is designated T to what looks like the negative first power. Not sure if you covered inverse functions in Algebra 1, but you definitely will see them in Algebra 2 and later in math. And you'll see that very similar notation. So the T to the negative first power really just means the inverse of T, in this case, the inverse of the transformation. And it has this property. So the inverse transformation takes the original point back to itself, or the image back to the pre-image. Now, we got real specific with our notation, specifically with translation, reflection, and rotation. And so when we talk about going in reverse order or undoing the transformation, the notation obviously changes just a little bit. So, for example, and these are just example functions, if we were saying translate by directed line segment AB, this is what the original notation would look like. But recall directed line segment AB, that means that's whatever AB is, that length, that's how far we're moving, and in that direction from A to B. But if we're going in the inverse, what you see here is that we're actually going to translate still that same distance. The length from A to B is the same as B to A, but we're now going in a different order from B to A. We're going backwards. That's literally why we're doing this inverse, the reverse or undoing of the transformation. Now, if you notice with the reflection, it's a little bit even more distinct than a translation. A reflection about some line L, notice the inverse is a reflection across that same line. For example, let's say we have an X and Y axis, and I take some arrow. We love to use arrows because we can see the direction. If I reflect that across the line X equals 0 or the Y axis, to undo that, I'll literally reflect across that same line, X equals 0. So that's why you see here the inverse of a reflection across line L is a reflection across line L. The last one, a rotation of m degrees about point O, which is typically the origin, by the way. If you haven't picked up on that, they usually refer to point O as the origin. So if the typical, let's say, rotating m degrees, the inverse of that is negative m degrees, or just the opposite. If it was negative m degrees, then the inverse would be positive m degrees. And hopefully that makes sense, and I can draw that one as well, representation of that on the X and Y axis. So if we have, again, let's say our arrow is pointing up, and we rotate that 90 degrees counterclockwise around the origin, it's going to end up somewhere in this ballpark. Again, we're not getting exact, but that was 90 degrees counterclockwise, which would have been a positive 90 degrees. And to go in reverse order, we would just go 90 degrees clockwise, which would be a negative 90 degrees. And so that's representing this information here, that whatever degree of rotation we rotate to do the exact opposite, we just make the negative form of it. Well, hopefully you're asking, how do we undo, or what's the opposite of 180 degrees? Well, because we don't have to specify positive or negative with 180 degree rotation, it will be the same. So maybe some of you are asking that question yourself. So if you would, go and draw a line above try these A. Look at the information here. It really just gives you all the answers, but they're hoping you digest the information. Read through it before continuing the video. So it's important to point out a couple things. Isosceles triangle A prime, B prime, C prime is the image. It's the image of one of these original triangles. And so our job is, based on the inverse functions of these transformations, is figure out which of these triangles was the pre-image. So they told us it is the image of this combination here, which means we rotate it around point O, which is the center of the triangle, 90 degrees counterclockwise. Remember, positive 90 degrees is actually 90 degrees counterclockwise. Then we translated using directed line segment BC. And so what we're seeing here, this triangle A prime, B prime, C prime, is the image. And so we're trying to figure out which of these three triangles is the pre-image of this image. So step one says find the inverse combination. So that's what we're going to do first. The inverse combination of a rotation around point O 90 degrees is a rotation around point O negative 90 degrees. That's what we set up here. So the center of rotation remains the same. We just change the sign most of the time, unless it's 180. We change the sign of our angle of rotation. So the inverse of 90 degrees is negative 90 degrees. And then our translation, using directed line segment BC, we will use directed line segment C prime B prime. Now, again, the reason it's C prime B prime is because this segment here is the image of CB. And so, again, we swapped BC because we're not going from left to right or right to left. We're going now from B to C to C to B. So the other thing I want to point out, and I kind of highlighted it here, not only do we invert the individual transformations, but we also invert the order. Notice the original order, we started with the rotation 90 degrees counterclockwise, and then we translated using directed line segment BC. But the inverse function tells us we're going to translate using C prime B prime first, then rotate 90 degrees clockwise. So with that in mind, we're going to translate using C prime B prime. So if C to B is actually pointing to the left, that's what we're going to do. And I'll kind of use a lighter color so it doesn't get too crazy. So that's where from C to B, imagine all these points remain roughly in the same general area of each other. And then we're going to rotate around point O 90 degrees clockwise. 90 degrees clockwise. Now, as I'm doing this, I'm actually recalling from last year when I went through this text, there is a slight error at the very end. If based on what they drew here, and I believe B and C prime should actually be swapped, but we'll just roll with it. Based on, if this really is the diagram, and I recall this from last year, the result is actually triangle 1. So if you see the direction we went to the left from C prime to B prime, and then if we rotated around this point, well, see, if we look at it that way, rotating 90 degrees clockwise would actually be over here. So I think that's why last year we swapped it up. So that's what I'm going to do here. I apologize for any of the confusion. You know, the book does have some errors from time to time, and I'm recalling that this is, in fact, the error. So if you would, scratch out these 2 points and replace them. We're going to swap this with C prime and this with B prime. It's going to make a little bit more sense why they said the pre-image is actually triangle 2. So now with that in mind, from C prime to B prime, we're going to the right that distance. So we'll end up somewhere in this general direction. That makes a little bit more sense. And then if we rotate 90 degrees clockwise, that tip of that triangle will actually end up at triangle 2. So I apologize. I remember that from last year, and then when I started performing this transformation, I recalled that we needed to make that fix. So go back and swap B prime and C prime. It's just going to make more sense of the direction they're taking here. But again, all confusion aside, when we go in the inverse, we're going from C prime to B prime, which is to the right, still rotating around the center, but now we're rotating 90 degrees clockwise, and we'll end up back where we began at triangle 2. Now looking at try these A, they want us to find a composition that maps triangle 1 to triangle A prime, B prime, C prime, and then find a composition that maps triangle 3 to triangle A prime, B prime, C prime. So take a second as we near the end of our lesson. Take a second, you can draw a line if you will, or if you want to, and try these A, and B. So on A, I really try to stick to it. You'll see I kind of did something fun, a little bit unique on B. But on A, so we're trying to map triangle 1 to A prime, B prime, C prime. So I said if we rotate 90 degrees clockwise around point O, so imagine triangle 1 rotating 90 degrees clockwise around its center O, and then translating use CB. So C would have been here, B would have been here, so we would move to the right that distance and in that direction. And that, of course, would map it onto triangle A prime, B prime, C prime. Let me kind of clear that up a little bit. Now, the other one I did, I just kind of probably threw you a curveball, but I imagined a line that ran directly between these two triangles, halfway between the two, to be exact, and parallel to the bottom sides of these two triangles. So I thought if we just simply reflect, and I called it line L, if we reflect over that line, triangle 3 will map perfectly onto triangle A prime, B prime, C prime. The book shows a little bit different, but in the same context, I just thought it made more sense to actually draw my own line, call it line L, and say reflecting over that line would map triangle 3 onto triangle A prime, B prime, C prime. So I know this lesson was pretty heavy, and it makes sense because now we're combining all the transformations. So feel free to rewatch any of these videos. If you have a question, reach out to me on Remind, or my hybrid students. Speak up in class if you have any questions. And as always, go to the learning target, reevaluate your understanding. These are the inverse functions, so hopefully we now have kind of an idea of what an inverse of mapping the image back to the pre-image looks like. So watch the video as needed and reach out to me, and thank y'all for watching.